Welcome to the Carl Sagan seminar series. Today is Wednesday, May 20th, 2009. And just want to let you know a few things before we get started here. And that is that these seminars are recorded, and you can watch them later at your convenience and find the link at the SETI.org website. And you can also look for them on YouTube and find the entire seminar series there. We ask, because they're being recorded, that you try to hold your questions until the seminar is done, just to avoid sort of gaps in the seminar itself. And at which time, after the end of the seminar, I'll come around with this recording device, which is what I'm holding here. It's not a microphone, and pass that around. So please wait and speak your questions into the recorder. Today we're I guess lucky to have a speaker from Berkeley, Edwin Kite, who's a graduate student in the Department of Geological and Planetary Sciences. And Edwin has a very distinguished background already for such a young investigator. He did his undergraduate work at Cambridge University in England and got lots of honors. And then came to UC Berkeley and has found actually he likes California, likes Northern California. So even though he had experience as a summer undergrad research fellow down at Caltech when he was a younger investigator. Today he's going to talk about the true polar wander and climate on late Hesperian, Amazonian Mars, and it's my pleasure to welcome him today to the Carl Sagan Seminar Series.
Thank you very much. Yep. First of all, I'd like to acknowledge my collaborators on this project. Isamu Matsuyama, who was at Carnegie throughout this project but has just moved to Berkeley. My advisor, Michael Manga, Taylor Perron, an assistant professor at MIT, and Jerry Mitrovica. And they're all co-authors on a paper describing this work, which just came out in EPSL last week. For follow-up work, which is still ongoing, Laurie Fenton, who's in this audience, Melinda Carre, and Jeff Hollingsworth from NASA Ames are all involved. What I'm going to propose to you today is that young volcanic load, shown in red on this projection, which shows both of the Martian poles, shifted the Martian pole relative to the lithosphere upwards along the green line, that this so-called true polar wander is recorded by the positions of paleopolar deposits, shown in the blue tints near the north and the pink tints near the south, and that this shift had significant implications for late Hesperian and Amazonian climate. What do I mean by late Hesperian and Amazonian? The last 3.5 billion years of Martian history, after early Mars, after the valley networks had ceased to form. True polar wander and its importance for climate have been of interest to scientists for some time. Hooke, one of the founders of the Royal Society, noticed that the fossils preserved in the cliffs of southern England were warm water animals. And given that southern England is hardly the warmest place on the planet today, he speculated about what could have caused this shift. We now know it's plate tectonics. Of course, Hooke didn't, and so he said, I suppose that the axis of the diurnal rotation of the Earth hath also had a progressive motion, and hath been changed in position within the body of the Earth, and consequently that the polar points upon the Earth's surface have altered their situation, and hereby a fruitful land may be turned to barrenness, as well as barren may be made fruitful. On Mars we don't really think in terms of fruitful and barren, but latitude is still a primary control on the geomorphology of the Amazonian, as shown by this slide taken from Jim Head's work. The coal-based glacial crater fill is found only polewards of 50 degrees north, and there are many other traces of past climate that show strong latitudinal control. Because polar wander shifts climate belts relative to present-day lines of latitude, it alters the tectonic boundary conditions for past climate reconstruction. And in addition, true polar wander may constrain the volcanic history of Mars because volcanoes dominate the load. Now, of course, this raises the question, did true polar wander actually occur? And testing that hypothesis is the subject of this talk. But first of all, what would it look like? The map of Mars, courtesy of Mars Orbiter Laser Altimeter. This is a polar shift of the effect of a polar shift of 10 degrees along the 165 east line. As you can see, Hellas is almost unchanged in latitude. Argyre, which shows evidence of heavy glaciation, is moved poleward, and Tharsis remains on the equator. With a 30-degree polar wander, Argyre moves close to the moves into very high latitudes. Tharsis still remains on the equator, and Elysium is moved to the high northern latitudes. So this is just an outline of the talk. So what is polar wander? It's the movement of the planet's entire lithosphere with respect to the spin axis in response to changes in mass distribution. Over geologic time, energy dissipation within a planet's viscous interior will align the spin axis with the maximum moment of inertia. It's important to understand the distinction between a load and the uncompensated part of a load. On a fluid planet, loads are fully compensated, so that there is only a very small geoid anomaly corresponding to the load. On a planet with a global, unfractured, and thick elastic lithosphere, as we believe Mars is, there is a degree of the load is not fully compensated. Alternatively, dynamic support by mantle motions can lead to geoid anomalies. These figures, by the way, are courtesy of my co-author Isamu Matsuyama. Positive loads go to the equator, and the Tharsis bulge is perhaps the best example we have, and negative loads go to the poles, and that's believed to be the reason why Enceladus's plume terrain sits close to the poles. Throughout this talk, I'm not going to consider the time-dependent aspect of true polar wander. I will assume that the true polar wander response timescale is much shorter than the geologic intervals we'll be considering. That's certainly a good assumption for Earth, and it's very likely to be a good assumption for Mars as well. In Earth history, true polar wander has played second fiddle to plate tectonics, with some exceptions. So the figure on the left shows a significant anti-clockwise shift in the in the Triassic, recorded by the apparent polar wander paths locked in the paleomagnetic drift of the rocks. And in this case, the continental drift rates as a result of polar wander actually exceeded, for a brief geologic interval, the continental drift rates as a result of plate tectonics. But that is the exception rather than the rule. However, on planets without plate tectonics, true polar wander comes to the fore. And I'm not the first to suggest this. In the late 1980s, based on Viking imagery, Schultz and Lutz suggested that equatorial antipodal layer deposits recorded a paleo spin axis on Mars. The antipodal deposits they were referring to were the Medusae Fossae Formation west of Tharsis, and the layered terrains in western Arabia and Schiaparelli crater. Mars Odyssey detected water-equivalent hydrogen local maxima which correlate with these deposits. However, I think there are two major problems with the hypothesis that true polar wander is recorded by these equatorial deposits. The first is that high obliquity can explain the observations. In the bottom left, you see GCM output from Mike Michner and Mark Richardson, which, although it doesn't agree with every detail, shows that waterized deposition maxima there's a lot of degree 2 power in the waterized deposition signature at high obliquity, which is also the case for the water-equivalent hydrogen maxima. And the second problem, and I think a conclusive one, is that Tharsis limits true polar wander subsequent to Tharsis formation, and these layer deposits post-date Tharsis emplacement. The top left is a gravity anomaly map of Mars. Tharsis sits at the center, and you can see it's the dominant feature in the planet's geoid. The bulk of Tharsis was in place before the valley networks, and any subsequent true polar wander that moves Tharsis away from the equator will be strongly resisted. However, it's still possible to have true polar wander, provided that it's along the Great Circle 90 degrees from Tharsis, in which case Tharsis will still remain on the equator. And that's shown by the figure in the bottom right. In the absence, this shows the response, the pole shift resulting from a unit mass emplaced at different latitudes and longitudes. So you're looking down the North Pole, and the arrows show the direction in which the pole shifts as a result of a unit mass emplaced at the root of the arrow. So you can see that in the absence of Tharsis, the pole simply moves in such a way as to move the positive mass towards the equator. And the amount of polar wander reduces as you get close to the pole. With Tharsis, shown by the black dot, the situation is completely different. In essence, you've lost 1 degree of freedom in the problem. Loads which tend to move Tharsis away from the equator produce minimal polar wander, but loads that tend to produce polar wander along the great circle 90 degrees from Tharsis can still produce significant shifts. And it's been suggested in a Nature paper by my co-author Taylor Perron, I wasn't an author on this paper, that true polar wander can explain the mismatch between proposed ocean shorelines on Mars and equipotentials. So in the top left panel you see the white and black lines, which are the proposed contacts, contact 1 and contact 2, proposed on the basis of Viking imagery by Parker et al. In 1993. Modal topography showed that these shorelines don't define an equipotential as expected for a coast, but polar wander can explain most of this mismatch. And moreover, the best fit true polar wander scenario that minimizes the mismatch of Parker's contacts with the shoreline lies close to the only permissible great circle along which true polar wander can occur, 90 degrees from Tharsis, which is shown by the top right figure, again from Taylor's paper. However, because there's some doubt as to whether the contacts mapped by Parker are in fact shorelines at all, I think that the ocean question is still unresolved. The polar wander interpretation helps to explain the mismatch, but the burden of proof still lies with the ocean hypothesis. So now moving on to our contribution. So this again is the figure from the first slide of the talk. The yellow dot is the center of Tharsis, and you can see that the area of young volcanism shown in red is offset to the west of that ancient Tharsis lode. So the elements of our hypothesis test were first to determine the magnitude of the young volcanic lode. Second, to calculate the true polar wander response to that volcanic load for different scenarios about Mars's geodynamic history. And thirdly, to compare with observations of the paleopolar deposits, mostly their location. So, on to the first part. We know the area to within a few percent. The ongoing revisions of the geologic map of Mars may shift some of these boundaries, but not by much. What we don't know is thickness. All of the methods that have been proposed have significant errors associated with them. So I'll just pick one of these 5 methods. The method of looking at the admittance and correlation between gravity and topography in principle can date the age of formation of the bulk of a volcano, not just its surface age. But in practice, there are significant concerns about the methods used, and the method depends on assumptions about the thermal history of Mars, which haven't been fully tested. So, to bracket these uncertainties, I assigned small, intermediate, and large thicknesses to every geologic unit in the young volcanic province. And you can see that the color bar is a log scale, and there is a huge difference between the small scenario, shown in the bottom right panel here, and the large scenario. So, for example, at Olympus Mons, this is the difference between assuming a thin drape of young lava over a Noachian core and assuming that the entire volcano, or the majority of the volcano, dates to the late Hesperian and Amazonian. So the total range in volcanic loads encompassed by these scenarios is about a factor of 10. Recent developments suggest that the low end of the low estimates is more likely to be correct. First, Sharad has mapped subsurface interfaces in Amazonas Planitia and west of and in Elysium Planitia, which possibly correspond to the base of the young lavas and the contact with ancient bedrock. Secondly, improved crater size frequency estimates using HRC data support the idea that the Amazonian-aged volcanoes on Mars have an Amazonian surface age, but retain a population of late Hesperian or even older craters, suggesting that the Amazonian resurfacing is relatively shallow. So the second part of our test is to calculate the true polar wander response to that volcanic load. We include the effects of a fossil rotational bulge, which will tend to retard polar wander, and the energy stored in the elastic lithosphere. We consider two main cases, one in which Tharsis forms close to the equator, and one in which Tharsis forms far from the equator. And so we find that where Tharsis forms close to the equator, the true polar wander response is geologically insignificant, at most a couple of degrees. So for the remainder of the talk, I'm going to focus on the cases where polar wander is geologically significant, outlined in the red box here. We find a maximum polar wander of slightly more than 33 degrees. So this isn't enough to explain the Schultz and Lutz scenario in which the layered deposits near the equator record polar wander. But it's still a lot. As elastic thickness in our models increases, so does the magnitude of polar wander response. But even for the smallest elastic thickness we consider, and even for the smallest load, we still see a true polar wander response of in excess of 6 degrees, which is geologically measurable. We also consider other scenarios in which different volcanic provinces erupt sequentially. So much for the forward model. What about comparison with observations? Paleopolar deposits have been suggested by Fischbau and Head, and also earlier by Malin et al. In a 1973 paper, to record past locations of Mars's spin axis. So these are cross-sections using Melo topography along the line of polar wander. Okay, thank you. Okay. Along the line of polar wander, and you can see that the youngest deposits are offset latitudinally from underlying and more ancient deposits interpreted to record the past positions of ice sheets. So here's the situation in the south. The southern residual cap, CO2 rich, is offset from the underlying SPLD, which in turn is offset from the Dorsa Argentea formation. Our forward model produces points, so I need to turn this geologic complexity into a point and an error bar for comparison. To do this, for each polar deposit, I mask out younger materials and fit a circle to the observed geology. So this is the result. The error bar, shown by the green circle here, corresponds to the average mismatch between the spin axis and the areal centroid of the present-day polar layer deposits. So the southern residual cap is offset by 2.3 degrees from the present spin axis, and the north polar layer deposits are offset by 2.4 degrees from the present-day spin axis. And this is exactly the same exercise in the north. So what you see here is the basal unit. Here the Scandia carbi, and here this box is the convex hull defining the Scandia tholi. Notice, by the way, that this green dot, which is the paleopole position calculated for the basal unit, is outside the convex hull of the basal unit. And that's just a result of the fitting of a circle to this small outcrop segment. And this has been confirmed independently. I only use geologic maps to define these points. By radar mapping, Sharrett has shown, firstly, that the basal unit extends underneath the North Polar layer deposits, and second, that it peters out approximately the location of Chasma Boreali and does not extend beneath the Promethei lingular lobe. And that's a good match to our circular fit. So Sharrett has independently corroborated the notion that paleopolar caps were approximately circular. So on this map I've plotted both the forward model calculations and the geologically inferred paleopoles. As you can see, the geologically inferred paleopoles, the centroids of the paleopolar deposits, lie along the, I suppose you could call it a racetrack, defined by the paleopole calculations. Now, as you can see, there are a number of paleopole positions that lie well beyond, but these correspond to the scenarios in which recent volcanism was very voluminous. So you should think of that as simply an upper limit for volcanism. And we don't need anything like the upper limit to produce the required magnitude of polar wander. So both magnitude and direction seem to agree. Here I've just plotted the results for the small load, A, medium load, B, and the large load for a range of elastic thicknesses. And you can see that even for the for an elastic thickness of 200 kilometers, which corresponds to the medium load, we can produce a geologically significant amount of polar wander. And matching the Dorsal-Argentia formation offset doesn't require even the medium load. The black dashed lines bracketing the racetrack here are just a way that I try to account for the fact that the Pedicle calculation is not perfect, especially where there isn't much outcrop. I'm trying to infer a large ice sheet from a small amount of outcrop, and the error associated with that I've estimated by the black dotted lines. So this is independent from the fact that polar caps don't track the spin axis precisely, and that source of error is shown by the green circles. This is the situation in the north, and again you can see that the youngest paleopolar deposits do lie along the racetrack, but we have a problem with the Scandia 30. The Scandia 30 paleopole does not lie on the racetrack, and I scratched my head for a while about why this was, and I have a two-part answer. The first is that young material, shown by the hachures here, obscures underlying deposits in the region close to 165 east. So it's possible and testable through radar that domes and mounds similar to the Scandia 30 and Cave underlie the 100-meter thick ice here. A second possibility is that the Scandia 30 have been misinterpreted and don't in fact record a paleopole. So if that's your preference and you're familiar with the geology in this region, mentally cross this green dot off your list. So to summarize our results, the hypothesis of late-stage true polar wander survives our test because we've shown that young volcanic loads inferred from geology are sufficient to produce the magnitude and direction of polar wander inferred from the locations of the paleopolar deposits. The required magnitude of volcanism is reasonable. However, geologically significant late-stage polar wander does require that Tharsis forms far from the equator. So there are independent tests that need to be done to check that assumption. The event shifts the boundary conditions for pre-polar wander climate, and we predict that this shift should have left recognizable geomorphic and perhaps tectonic signatures. We're pursuing the geomorphic signature angle. At the moment, we haven't started looking for fault reactivation associated with polar wander. That's certainly another test that one could pursue. The figure here just relates the magnitude of polar wander to the total volume of late Hesperian and Amazonian volcanism for a variety of different assumptions about the elastic thickness of Mars. The present-day elastic thickness of Mars is 300 kilometers, so you can see, at least at the poles. So you can see that even a small volume of volcanism is sufficient to produce a large magnitude of polar wander. But what matters in driving polar wander is the elastic thickness at the time of emplacement of the volcanic load. So that might be thinner, perhaps 100 kilometers, as inferred for the emplacement of as inferred for the elastic thickness at the time of the emplacement of Tharsis, in which case a somewhat larger, but still reasonable, volume of volcanism is required. So I'm now going to move on to looking for geomorphological traces of polar wander. So I'm now moving from the part of our talk which has been peer-reviewed and published to the part that is still in progress. So first I'd like to draw your attention to a couple of post-Hesperian climate puzzles. The first is the roughness of Mars as measured from molar. So molar spots are laid down at an interval of 300 meters. So the shortest roughness length scale that is meaningful is 600 meters. At that baseline, it's very clear that Mars is rough at low and medium latitudes and smooth near the poles. This has been known for a long time. So that's the first order observation, a strong latitudinal control on roughness. This is not associated with the young Mansell of Mustard et al., and it is not likely to be the result of the recent ice ages so well described by the Brown University group. The evidence for that is that 600-meter baseline rough craters in the northern plains show extensive mantling and polygon formation. So they've been affected by the recent ice ages, but that hasn't been sufficient to smooth them at 600 meter baseline scale. So that's the first order observation, but an important second order observation is that the latitude of the rollover from rough to smooth varies between hemispheres. In a hemisphere centered on the Martian meridian, it's at relatively low latitudes, this line. At the hemisphere centered on roughly 180 east, the rollover is at roughly 45 degrees latitude. And this has been known for a long time, but no explanation has been available. It certainly doesn't track present-day temperature, and the lines, the latitude belts defined by the young mantle, by the location of gullies, and by the roughness within a molar spot, so the pulse width of the return, closely trace latitude belts. They do not show this hemispheric asymmetry. A second observation is that vent effects at the Mars Pathfinder landing site are misaligned with present-day winds. In this rosette diagram, the white arrow shows the direction of present-day winds as output by a GCM, the strongest present-day winds. The black arrow is the mean position of about over 100 vent effects. So there's some scatter about this, but it's roughly west. And the black rose plot shows the direction of elongation of craters, so the direction of preferential erosion of craters near the Mars Pathfinder landing site as measured from Mars orbiter camera images. So there's a mismatch here. This mismatch cannot be explained by obliquity, and it was suggested by Herbali et al. In Icarus in 2003 that having ruled out all the obvious possibilities, true polar wander might be involved. So to see if true polar wander can account for these anomalies, we're using the NASA Ames GCM with paleopolar topography, backrotating the output to present-day coordinates and comparing with the geologic observations. So today I'm just going to talk about the first anomaly, the hemispheric offset of the latitudinal climate belts. We will predict that backrotated pre-true polar wander temperature contours should be parallel to the edge of the smooth terrain. That's because the smoothing process almost certainly involves ground ice, high temperatures, or both, either through ice creep, which is sensitive to mean annual temperature, or through periglacial solifluction, downslope movement of thin layers mobilized by transient liquid water, which is sensitive to maximum temperature. So here are preliminary results. This is the annual mean temperature field. We've only run 3 cases so far. This is the control case. This is the backrotated polar wander case. For our paleopole position, we use the geologically inferred paleopole for the Dorsal Argentea formation, which is the oldest, the most displaced, and the least likely to be accounted for by meteorological effects. So it's offset by 8 degrees from the present-day spin axis. And the amplitude, as you would expect, the amplitude of displacement, the peak-to-peak amplitude, is about twice 8 degrees, or 3 GCM grid cells in this case. And both the longitude and the magnitude of the displacement compare well to the offset of the rough-smooth boundary at the 600-meter baseline. So this is good. The next slide displays the results for maximum temperature, and you can see the same pattern. These are actually GCM grid cells. So north is up, and I'm afraid west is that way. So the axes, the east-west axes are flipped here. If you're looking for Hellas or Tharsis through the lapse rate. Okay, and this is the same map for maximum temperature. And as you can see, there's a very strong southern hemisphere bias because we're running with the present-day longitude of perihelion. But the thing I'd like to draw your attention to is that if one were to try and fit belts of constant maximum temperature they are displaced by about 3 grid sols again in the back-rotated polar wander case. So, in a sense, this is exactly what we'd expect. Most of the difference between these two maps is the result of the back rotation. So what we're seeing is that shifting the positions of the volcanoes and of the major basins by about 8 degrees, a maximum of 8 degrees, doesn't change Mars's, doesn't change the basics of Mars's general circulation. However, we are still analyzing the wind field results, but I won't discuss those today. So, finally, in conclusion, the hypothesis of late-stage polar wander survives our test, provided that Tharsis forms far from the equator. If Tharsis formed close to the equator, surface loads are very likely insufficient to drive geologically significant polar wander. So, if polar wander occurred, it would require internal loads, such as changes in mantle plumes. Because polar wander shifts the boundary conditions for pre-polar wander climate reconstructions, it is worth simulating climate under pre-true polar wander conditions, in part to see if true polar wander can account for certain climate anomalies, and these simulations are underway. The first part of our talk, not the GCMs, but the hypothesis test, has been published. It's in the 15th of April issue of EPSL, and I direct you to that for more details about the geology. But I have plenty of backup slides, and I'd be happy to take any questions.
So what would it take to put the pole at the equator to explain Schultz's observations? Is that physically ruled out because of the volcanic loads?
I think the right thing to say is that the deposits aren't really in the right place. So they certainly postdate Tharsis. The Medusa Fosse Formation certainly postdates Tharsis. The Arabia-led deposits almost certainly postdate Tharsis. So here we go. The Tharsis is centered at 226 east. So 226 plus 90 puts you at about 330 east. And as you can see, the Arabia deposits aren't at a place that would be shifted by the pole, whatever the size of your load.
So is it still possible then you could have true polar wander go all the way to the pole, just not in the spots that Schultz sees it? Excuse me, all the way to the equator?
I haven't done a full analysis of internal loads. We're going to. So the back of the envelope, sort of just taking the size of mantle plumes from published calculations, the temperature anomaly, the density anomaly, certainly not. But I haven't done a detailed analysis, but that's my first cut. I've actually had an extensive email conversation with Paul Niles about the hypothesis of polar wander that he puts forward in his recent Nature Geoscience paper. I think it weakens his hypothesis unnecessarily. High obliquity is sufficient to put lots of ice on the equator. There's no need to appeal to polar wander. And indeed, high obliquity, at least in some GCMs, puts the ice in roughly the right place, dependent on various parameters such as the ice fall rate.
I'm thinking more about the Pathfinder wind directions. I think it's going to take more than 30 degrees to match those.
Then it's still unexplained. But can I just follow up on that? The presence of, for example, a 3 kilometer thick ice sheet at high obliquity will certainly reorient wind patterns in areas adjacent to the ice sheets. And if you're going to say that the hematite deposit at the opportunity landing site is associated with an ice sheet, as Paul Niles and Jim Michalski would have it, then you have a potential way to reroute winds in that vicinity. So, of course, the Laurentide ice sheet shifted the jet stream 15, 20 degrees south at the last glacial maximum.
If this is a naive question, if this is true polar wander, what's false polar wander?
Apparent polar wander is what's recorded by Paleomag for most of Earth's history. So, taking you to the Earth slide, most of the time, apparent polar wonder tracks are actually recording the motion of subsets of Earth's lithosphere with respect to the spin axis. But the lithosphere as a whole tends to move remarkably little. When the lithosphere moves coherently, so when all the paleomag tracks are consistent with the net rotation, that's when you assign it to polar wonder, like this Triassic interval here.
Actually, Edwin, I wonder if, just for the audience, if you could give us sort of a general sort of recap of the description of how polar wander supports the ancient ocean
Sure, yeah.
shoreline.
Yeah, definitely. So the reference for this is Perron et al. Nature 2007. I wasn't a co-author on this paper. The hypothesis of an ancient ocean on Mars is beset by many difficulties. The first is the absence of obvious ocean deposits in the northern plains. What we see is heavily glacially reworked, and there is at least the suggestion that underneath those heavily glacially reworked Vastus Borealis formation, there's just Hesperian basalt. But there is the suggestion that shoreline features, best seen in Viking imagery, and which actually tend to dissolve when you look at higher resolution imagery, trace out the ocean. Now, what I just said sounded skeptical, but I don't mean it that way. Often in the field, when you walk up close to an outcrop, you can actually lose the sense of the larger picture that you can get from standing 50 or 100 meters away. So Viking images may simply be the best way to trace out these shoreline. This is the so-called Deuteronolis shoreline, and this is the Arabia shoreline, the black line. These are both from Parker et al.'s work. So what Perron et al. Did was took the deviation of these contexts from an equipotential and saw how true polar wander would have shifted the topography. So the basic idea is that on a fluid planet, when you reorient, you simply relax to the new equilibrium position. So there's no change in topography. However, on a planet with an elastic lithosphere, that relaxation is incomplete. So part of the rotational bulge from your pre-polar wander position, which on Mars, the equatorial minus polar radii is about 20 kilometers similar to Earth. So part of that 20-kilometer bulge is unrelaxed. So when you shift the poles, you also change the topography. A blackboarder would be really helpful here. So the overall... Oh, okay, fantastic. Okay. Okay. Oh, okay. Oh, this looks promising. Great. Okay. Yeah. Okay. So no, 30 degrees. Yeah. In terms of the load required for 30 degrees, our high case volcanism is sufficient. The whole of Elysium considered alone is sufficient. The load of the oceans is not in the right place. Taylor tried hard to use the ocean load itself, so the load required to fill the northern plains up to the level of Parker's contact to explain the polar wander, and found it insufficient. So just a quick explanation of that unrelaxed rotational bulge. So this is the pre-polar wander situation, and this is the post-polar wander situation. Because the with an elastic lithosphere that's 200 kilometers thick, which was the number used in the Perron et al. Paper, membrane stresses act to resist the relaxation of the fossil rotational bulge, the so-called relict or remnant bulge. And so topography here is higher than relative to the geoid, relative to the equipotential, than it is in the pre-polar wander situation. The shift in topography is strongest at degree 2, order 2, so quadrantial geometry. So that's, I mean, the 2-2 harmonic is basically this. So if you want to think of it as a football breathing, this is the geometry of the panels that are breathing. The resulting, so that's the basic idea. That's how you change the positions of shorelines with polar wander. And the surprising result, that is the reason it's a Nature paper rather than an Icarus paper, is that the best fitting paleopole position to reconcile the shorelines with an equipotential lies exactly along the, lies very close to the track along which polar wonder must occur after Tharsis forms, which is the result in the top right panel.
Edwin, you've talked about evidence for glacial geomorphic evidence and now oceanic. Do you have any fluvial evidence or paleofluvial evidence that might support this? I'm thinking primarily, although you may certainly have your own thoughts. I was thinking a bit of the inverted channels, the Hesperian age inverted channels that have been observed.
So is your idea that precipitation is stronger nearer the equator because there's more sunlight to dry?
I'm not actually sure what the idea is, just that I know that around this time there are all these inverted channels now popping up in equatorial locations, and I wasn't sure if that fit in any way with your hypothesis.
I think they're very interesting. I have ideas about them. They don't have to do with polar wonder. This might be a good time to mention that people have also tried to use the Martian magnetic field to construct polar wonder paths. But this is an early Mars problem rather than a late Mars problem. To address the sinuous ridges, valley networks valley networks are found most overwhelmingly at low latitudes, but it's not clear whether that's an artifact of selective preservation. Sinuous ridges seem to be found throughout the southern highlands without as strong a latitude dependence. But Devin, you know more about this than I do. The blue dot. So these are paleopole positions constructed by different methods. By different authors. So the Langley and Quenelle are actually using a method to produce the blue dots, and other authors, I think this is Arkani Hamed's positions in the green, and the black and white are still other authors. But the method of all four groups is the same. They're trying to define paleopoles on the basis of the mag on MGS. The problem is that in order to define a paleopole, you need a coherent patch of magnetism. And these do appear in the mag maps, which are from the Mars Global Survey at 400 kilometers altitude. But using the electron reflectometer part of the MGS MAG-ER instrument, you can actually construct a map of magnetic field intensity at 180 kilometers altitude, which is roughly the height of the Martian ionosphere. When you compare the two, a lot of the patches that you can see in the mag map on which these paleopoles are defined disappear. So I think this is an unsatisfactory method. And I'm sure Rob Lillis will tell you a lot more about that in 2 or 3 weeks for his talk efforts for down there.